So we've talked about the idea of distributions for individuals. And we've said we can think about the measure of central tendency, either the mean, the median. We said we the measure spread with the standard deviation, for example. And we drew a lot of pictures. And we said histograms that we can think of as individual people. We can also think of them in terms of probability. So with this, for example, if we have a nice normal distribution, we can say if the mean is here and the standard deviation is here, what's the probability of seeing certain values? So if you knew, for example, that IQ had a mean of 100, sorry, that's a mistake. This should be a mean mu of 100 and a sigma of, say, 15. Well, we can label this here, 100, 115, and so on. And we can say, what's the probability of getting certain values? Now, we're going to extend this concept, and this is a little bit weird, is we're no longer going to talk about individual people. We're not going to talk about, say, weightlifters, or we're not going to talk about someone's bone mineral density, but we're going to talk about the behavior of statistics. So we're going to start to talk about things like the behavior. It sounds weird, but the behavior of means. And once we get a good sense of how means behave, then we're going to be able to do two very important statistical concepts, the idea of estimation and then the idea of hypothesis testing. So let's get into a little bit about the behavior of means. We have to introduce this so that we can start to build evidence for cause and effect. And again, we're going to do estimation and hypothesis testing. And hypothesis testing, as we talked about this idea, statistics is backward. First, you assume some null hypothesis or a straw person that you wish to disprove. Then you take your data and say, what's the probability of getting my data if the null hypothesis were true? This is called the p-value. And then we take that p-value and we compare it to some cutoff. We call that the alpha level. What is that criterion for weirdness? And if the p-value is less than alpha, if things are really weird, we would say we reject the null hypothesis. So in order to build up to that, we need to think a little bit about how means behave. And the first concept here is that a mean is going to be a random variable. And this is a bit of a mind bender. Most people think that a mean is a number. I take everybody in the class, I add up their height, I divide it by the number of people, and that's the average height. It's a number. It's a real number. That's true. But if you think about why did you end up in this class? Why not a different section? Why not a different school? Why not next year? A little bit of why you ended up in this class is random. Some elements of chance played their role in that. And so the mean of the height of the students in this class, it's true that it's a real number, but it's also, we need to think that it's somewhat random. And we'll talk about this in a second. So let's introduce some terms. First of all, we need to be very careful about whether we're talking about a population or whether we're talking about a sample. In statistics, we all take samples, and we take that smaller sample and we want to make a statement to the larger population. The numbers that we use to describe our sample are called statistics. This is easy to remember. It's S and S. The numbers that describe the population, we use the word parameter, P and P. And we saw this before. We use Greek letters when we talk about parameters. So the mean of a population, we would use the letter mu. But the mean of a sample, we do X with a little bar on top of it. It should look like this, and it's called X bar. The standard deviation of your population, we use this Greek letter sigma, and we use this letter S for our sample. So when you see Greek letters, you know you're talking about the population. What is the population? Well, the population might be the population of the US, and I might take a random sample of that somehow. Or the population might be African American women aged 45 to 49 living in North Carolina, and I might take a random sample of that somehow. But the numbers that describe the population are parameters. Those that describe the sample are statistics. Now, we're going to start with the idea of using continuous variables. It's a little easier to see, but we can create a sort of distribution and talk about how these random variables behave. So what is a random sample? I just used that term. A random sample is, or a simple random sample is that every single person in the population has the same probability of being chosen. There aren't any people who are left out. There aren't any people who are more likely to be chosen because they're raising their hand a little bit higher or something like that. Everyone has an equal probability. Also, there's independent sampling. So if you get in the study, you can't say, I'll only be in the study if my friend Kevin is in too, and you guys come together. That's not independent. So in statistics, we always assume for now that samples are random. In epidemiology, you'll spend a lot of time thinking about what happens when samples are biased or when they're not independent of each other. So let's take a couple examples of random variables. Flipping a coin. If I said, flip a coin, what are you going to get? Well, you know it's 50% heads, 50% tails. But on a given flip, you're only going to get one or the other. A random sample of that would be to flip a coin 50 times. N equals 50, N being our sample size. If you sit there and flip a coin 50 times, you can hit pause and do it right now. How many heads will you get? Well, don't say 25 because you really don't know. You don't know exactly how many heads you're going to get until you take that sample. And that's the idea of a random variable. If we all flipped a coin right now and came back next week and said, how many heads did you get? We would get a distribution. Some people get 25, 24, 23, 30, right? We would get a distribution. Another example, I like this one, is the idea of how long does a light bulb last? We don't know. You can't go to the store and buy the light bulb that lasts the longest. There is some sort of variability in it, right? Not all light bulbs last the exact same amount of time. There's got to be some sort of average. There has to be some sort of population parameter, a number that describes the average length of a light bulb. But some are a little bit shorter. Some are a little bit longer. It's probably normally distributed. If you wanted to, you could go to Home Depot or Lowe's, Walmart, and you could grab 10 light bulbs. And you could go set them up at home. Maybe you have a fancy little makeup mirror and you got the 10 bulbs. And you could sit there and then you could calculate what is the average of my light bulbs. X bar equals whatever. That's a little messy. Let me write that again. But for the average, X bar equals whatever number of hours. What will this be? You don't know. It's random. You don't know until you actually go and you actually get the bulbs and you measure it. And so this is the idea that a mean is some sort of random variable, and you're not going to know the value until you actually take that sample. Now, we'll get more into that soon, but I just wanted to share this. I'm sitting here in May 2020 during COVID-19 quarantine, and this is a link of a website to a light bulb in California, the world's longest burning light bulb. It has been burning since, well, it says 117th year of illumination. And you can see as of now, it is still burning. So you guys can go check that out and see if it's there. And in the next set, we will talk about the behavior of these random variables.